Okay, I know you're looking at this video and you're saying, that's too many words already. Yeah, it's applications time, and this problem has a lot of words. So let's read through it. Let's highlight important information and figure out what's going on. So, after running out of prepackaged supplies, a nurse in a refugee camp prepares an intravenous sugar solution for the patients. If I knew more about medicine, I could tell you why they want a sugar solution. They mix 5 pounds of sugar into a large mixing tank that has 100 gallons of distilled water. Let's use that real quick. 5 pounds of sugar into a large mixing tank that has 100 gallons of distilled water. Okay. So 5 pounds of sugar in a tank with 100 gallons of distilled water. That's probably important. So write it down. There's also a tap that's pouring 10 gallons per minute. So this is a rate, right? 10 gallons per minute of water into the tank at the same time that sugar is poured in at 1 pound per minute. So we're adding 10 gallons per minute of water and 1 pound per minute of sugar. That's probably also important. Find the ratio of sugar to water given in pounds per gallon, that's like concentration, after 12 minutes. Okay, so this is a very common application of rational equations, rational functions, in that, oh, my upstairs neighbor is vacuuming. It's very loud. Anyway, this is a common application of rational functions. One thing divided by another thing, ratios, concentrations, rational functions pop up everywhere. Okay? Whenever we're comparing one thing to another, a lot of times we do that with fractions. So it wants to find the ratio of sugar to water after a certain amount of minutes. So that's a tall ask, right? It's asking us to model something for sugar and model something for water and then put them together. Well, let's do it separately first. Okay? First, let's just look at water. How is the water changing over time? So originally there's 100 gallons and we're adding 10 gallons per minute. How can we write that down? Right? 100 gallons at the start and then 10 gallons every minute. Well, that's a line. We can write that, if we wanted, as a function called W. W for water. W for winning. W of t is we started with 100 and we're adding 10 every minute. W in gallons, T in minutes. Now do the same thing for the sugar, okay? Pause the video, write down what you think the equation is going to be for sugar. What you should have gotten is sugar, let's call it S, capital S. Well, we started with 5 pounds of sugar, and we're adding 1 pound of sugar every minute. So S is going to be in pounds, and again, T is in minutes. So it wants us to look at the ratio of sugar to water in pounds per gallon. So pounds per gallon, this concentration, let's call it C of T, is in pounds per gallon. That's sugar divided by water. What's sugar? It's S of T. What's water? It's W of T. So the concentration is just sugar, which we said was 5 plus T, divided by water, which is 100 plus 10T. This is our concentration formula. So a rational function just comes from us looking at two different polynomials and just comparing them. All right. And specifically, the question's asking, what's the concentration after 12 minutes? We'll just plug it in. 5 plus 12 divided by 100 plus 10 times 12. That's going to give you 17 over 212, I think. Nope. Not. 120 plus 100. So that's 220. I don't think that reduces. What is that? What is that approximately equal to, right? This is pounds per gallon. That's our answer. What is that approximately equal to? Let's use, plug that in. 17 divided by 220. That's approximately 0.0773. It's about 0.0773 pounds per gallon. And eventually, what do we think is going to happen? This is the end of the problem. This is really the end of the video. But we started off with 5% sugar. Like, that's not percent. 5 pounds for every 100 gallons, 1/20th, 0.05. Right? We started off with 0.05 pounds per gallon. What's going to happen eventually? Well, eventually, all that matters is this. Eventually, it doesn't matter what we start with. It only matters what we end with. Eventually, we're going to have 1 pound per every 10 gallons, 0.1 pounds per gallon. Let's look at this function. Again, this is the end of the problem. You don't have to watch this, but I just want to connect a bunch of cool ideas. This is all related to each other. Okay. So if we write this function, right, 5 plus t divided by 100 plus 10t. Then we need to fix our scale, definitely. So go over here to this thing. Let's start at 0 minutes. And let's see what happens after an hour. And again, we only care about the concentration. The concentration is always going to be pretty small. Let's start at 0.2. I said the concentration should start at 5 pounds per gallon for 100 gallons. That's 0.05. Good. And eventually, as time goes on, let's see. At our 12 minutes. Our 12 minutes is this guy, right? I can't get it. But I could if I wanted to, right? T equals 12. Desmos actually wants me to type in X. You can see that other point, that concentration after 12 minutes. But in general, we can see as time goes on, right? What are we really getting close to? Really getting close to 0.1 as our concentration. We could zoom out even more. Go as far to the right as we want, right? We're getting really close to that 0.1. A horizontal asymptote. End behavior. It all ties together. Let me know if you have any questions. Bye-bye.